Hello and welcome to Empowered Learning. This is the first video in the Logic Theory video series. And so this video will serve its purpose as just getting you familiar with what logic is in general, going over what statements and connectives are, going over the 5 fundamental connectives and doing the truth tables for each of those, and then using that to be able to form a truth table for converse statement, inverse statement, contrapositive statement, in addition to a conditional statement, and to notice which of those forms of a compound statement are equivalent to each other and which of those are not. So let's go ahead and get started. So we know the root of mathematics is found in logic. So all of mathematics is based upon logic. And so this is one of the reasons why math is popularly known as an exact science. Its logic foundation gives it that characteristic. And of course, at the heart of logic is this question: is this true or false? And what I mean by this is whatever it is that we are talking about. However, the precise meaning of true and false can take on many forms. So for instance, in the world of electrical engineering, true may mean power on and false may be power off, or it could be coded just the opposite. So true could mean power off and false could be power on. And so we see that this abstract nature of logic allows it to be used in various fields and areas, and even in language arts. Now we will look into the basics of logic theory and how we can use it to decode the things that we see or hear to truly determine whether something is indeed true or false. And so, of course, at the heart of everything, we want to know, hey, is the statement that we come up with, is it going to be true or false from a logical standpoint? So the first thing that we need to talk about is statements and connectives and how we actually use those. So we know that logic is the theory of decoding statements. So that's what goes in this first blank here. And logic is the theory of decoding statements to see whether they are indeed true or false. So I'll change the color here. So true or false. Now we know that a statement is a declarative sentence. So for those of you that have forgotten a little bit about your English classes, a declarative sentence is basically a sentence that states an idea that ends in a period. So I'm going to erase this part because it doesn't, matter of fact, I think I'll erase all of it because it doesn't look too good. So I'll just put statement here again. And we'll put declarative. Trying to make that actually look a little better. All right. So in logic, we abstractly look at statements by replacing these statements with lowercase letters such as P, Q, R, etc. And so in logic, we know that the idea of the statement does not matter. Okay? So, and of course, we want to avoid that because, the idea, depending on what it is, may be something that may be something that you believe in, something that you don't believe in, something that may be part of your reality. It may not be in your reality. Some people may think it's immoral, whatever the idea is. And so logic cares about none of that. All that it cares about is whether the statement is true or false. And of course, as I've said before, declarative sentences are sentences that only end with a period. And so we're going to see some examples of statements, and then we're going to see some examples of some non-statements. So let me scroll down here. So examples of statements. Heart disease is a leading killer in some minor ethnic groups in the USA. If you eat more and exercise less, you will gain weight. and Warren Buffett and Oprah Winfrey are both billionaires. So in all of these, we have made a statement, and the statement is about an idea. And the only thing that we can say to this is whether what we've just said is true or false. Okay. Now, some examples of non-statements. You're fired. Okay. This is an example of an exclamation. We know it can't be a declarative sentence because it ends in an exclamation point. Next one, when did the team cross the finish line? We know that this can't be a declarative sentence type of statement because it has a question mark on it. Go to work. So for this one, although this ends in a period, this is what we call a command. And of course, a command, we can't ask whether that's true or false or not. So, of course, we can't even say that we're going to follow the command or not, but it's just a command. So it doesn't warrant something that can be looked at as being true or false. So these type statements, logically, we cannot evaluate. But these type, where their statements are just ideas and all that we can say about them is whether they're true or false, we can evaluate and look into further from a logic standpoint. So now we're going to talk about the difference in between simple and compound statements. So a simple statement only contains one idea. Okay, and I'll make that look a little better. Only contains one idea, where a compound statement contains more than one idea. And so as an example here, we have those same statements that we saw before, and we're going to decode whether these are simple or compound statements. And the reason why we're doing this is that when we logically look at these later on and replace these statements with lowercase letters, it's important for us to be able to identify what a statement is, and within a statement whether it has one idea or several, because we need to represent each idea with one of those lowercase letters that we talked about earlier. So the first one, heart disease is a killer in some minor ethnic groups in the United States of America. That will be a simple statement because it only contains one idea. For B, if you eat more and exercise less, you will gain weight. That is an example of a compound statement. And the reason for that is the first idea is if you eat more, you will gain weight. The second idea is if you exercise less, you will gain weight. So you see we have two ideas woven into that one statement. So that's why we call it a compound statement. Similarly, C is going to be a compound statement because we know that the two ideas for C is Warren Buffett is a billionaire, and the second idea is Oprah Winfrey is a billionaire. So together, both Warren Buffett and Oprah Winfrey are billionaires. So for D, this is also a compound statement. And this is because, again, we're saying that Mark Cuban is two things. We're saying that he's a business owner as well as a venture capitalist. So in knowing that, we have those two ideas, so this is a compound statement. Now when we get into actually trying to represent these statements in an abstract sense, in order to logically evaluate them, the first thing that we have to understand is that compound statements use these things called connectives to combine several ideas into one statement. Okay. So when we have more than one idea in a statement, we're going to use connectives. And so in the world of logic, a connective is a lot like an operation in normal math. So for instance, our basic operations in normal math are addition, we have subtraction, we have multiplication, depending on whether you write it with the X or the dot, and we have division, whether you do it like this or with the slash. And so in the world of just real number arithmetic type of math, then these are our quote unquote connectives in that world, but we just call them operations. Also, if you checked out my set theory videos, you notice that the operations in there are stuff like union, intersection. If we had some set name B, it would be the complement, whether we write it like this or like that. And we had the difference operator. So let's say if we wanted everything that is not in set B with respect to the universal. So we could also call these connectives as well, but these are normally called operations within set theory. But inside of logic, we don't call them operations, we call them connectives. Okay, so that's my point in elaborating on that. So the connectives here are word or phrases like and, or, not, if something, then something else comes as a result, or if we state one thing, let's say something happens if and only if something else happens. So these are the 5 main words or phrases that we have to create a logic operation for, which we're calling it a connective. And of course, we are going to take those word connectives and replace them with symbols. And so the table that I have here below, and I'll go ahead and scroll down and show it to you, is giving you a sense of what the 5 connectives are, as well as how they're related to set theory and normal mathematics or arithmetic type of mathematics. So our first connective is a conjunction connective, mainly talking about the word and here. And in normal math, the equivalent of that, not the exact same thing, but the equivalent of it is multiplication. In set theory, the equivalent of that would be intersection. And again, when I say equivalent, I don't mean it does the same exact thing. It just within that math space, it has the same type of function, or it acts the same way. And of course, in logic, for what we're studying now, this is going to be the symbol for it. Okay? And of course, the meaning of this is if both of these statements are true, then that is the only way that the compound statement itself is true. Okay? So for instance, I'll use this as an example. If a person gets the project done and they work 20 hours overtime, then they will get overtime pay. So that's an example of it, because in order for the person to get the overtime pay, they need to finish the project as well as put in the hours. Okay? Now for a disjunction, it's a little different. And of course, a disjunction is based upon the word or, and that acts like an addition symbol in normal math. It acts like union if we were talking about set theory, but in logic, we see that it's going to be this symbol. It looks like a little V or upside down TP. And of course, for the or connective, it means that if either P is true, or if Q is true, or if both are true, then the whole entire statement is true. Or put another way, if at least one of the 2 statements here are true, then everything is true. Okay, and I'll use my same example before, and I'll say if the project is completed, or the person works 20 hours of overtime, then they will get the overtime pay. So in this instance, we could have a person that, of course, puts in the 20 hours and they get the overtime pay, or they can work on the project for 5 hours and finish it, and they still get the same amount of overtime pay. So that's different than what we talked about here when we said that that person had to put in the 20 hours as well as finish the project in order to get the overtime pay, and both had to happen in order for the whole entire statement to be true. Now next we have our negation connective, and of course in normal math we know that by a negative sign, okay, which is a unary operation, not to be confused with a subtraction sign here, which is a binary operation. So there's a slight difference in between that. So when we say a negative sign, we mean like -2 there, okay? Whereas a subtraction sign may mean 3 minus 2. Now, within set theory, the equivalent of that is a complement symbol, which if we had some set A, it would be written as A complement or A complement this way with the little C in the exponent spot. In logic, this is a tilde sign, okay? And so we look at the negation as the opposite in this case. So if we have a statement P that actually is true, then the negation of P is false, and vice versa. If we have a statement P which is false, the negation of P is true. So let's move on and see our last two connectives. So for the last two, we have a conditional connective, and so this is our normal if-then statement. And in normal math, we actually use it that way as an if-then statement. And for set theory, the equivalent of that would be like subset. Okay, again, not exactly the same, but it has the same type function. Within logic, we use this arrow here to say if this thing over here, then that thing over there. And we know that logically, we know that an if-then statement is true in all cases, except for when the if part of the statement is true, but the then part is false. Okay, and we'll talk about that a little bit more when we form these truth tables a little bit later. Now, for the biconditional statement, it's an if and only if type statement, and I'll give you an example of that to sort of elaborate on the conditional and the biconditional statement from a math standpoint, so that you can kind of see what see how it actually is. But the biconditional statement in set theory kind of acts like the equal sign, okay? And in logic, we do it with the double arrows. So you see the conditional statement just goes from left to right, whereas the biconditional statement goes both ways, okay? And so for a biconditional statement, the only way that this whole entire statement is true is if, of course, the conditional statement here is true and the conditional statement here is true. Or put another way, as we'll see when we do the truth tables a little bit later, both P and Q have to be true, or both P and Q have to be false in order for that to happen, okay? So as an example of trying to elaborate on a conditional and biconditional statement, I'm actually going to start with a biconditional one. And I'm going to say this. If a line has a slope equal to 0, then the line is horizontal. And so this is actually a conditional statement. So here, line has a slope of 0, that's going to be my P. The line is horizontal, that's going to be my Q. So I can really write this as a if P then Q statement, okay? Now, to show you what a biconditional statement is, I'm going to reword this way. It says the slope of a line is 0 if and only if the line is horizontal. Okay. So here we see this statement here is the P, this statement is the Q, and we would rewrite this way in symbol form. Okay. Now, we'll also find out that this statement here can be broken up, and we could say that the conditional statement, biconditional statement rather, is just this statement here, a conditional statement going from left to right, and then another conditional statement going from right to left, so to speak, and those two statements are ANDed together. Okay. All right, so moving on here, one other thing that we want to note is that whenever we use parentheses or another type of grouping symbol in logic, we actually use that just like how we would in normal math. In other words, to set the order of operation, or in this case, the order of connectives that we'll use. So it just gives us an order into which we need to do things. And of course, in the English language, this grouping symbol is equivalent to using a comma. Okay? And so that statement was just made just to make sure that all the things that we know for order of operation, as far as what operation has hierarchy over another one, we're going to learn those type things here as well. So the basis for analyzing compound statements using connectives is using truth tables. And so we're going to go over this, what a truth table is, what it looks like, and what it does to help us. So at the end of the day, truth tables are used to determine if compound statements are true or false. So again, the main focus is to figure out if a statement, whether it's a simple one or compound one, is going to be true or false. And so now what we're going to do is figure out how to form our truth tables here. So we have our 5 fundamental connectives. And so one of the things that we need to know for our truth table is, how do we actually come up with the number of possibilities that it could be for a compound statement or a single statement. And so the number of single statements in a compound statement determines the number of rows in a truth table. And so if you let, let's say, the variable k equal the number of single statements, then we know that the number of rows in the truth table is equal to 2 raised to the k. Now, for those of you that have watched my set theory videos, you know that this is also the same exact formula for figuring out the number of subsets that a set has. And so the reason for that is that the number of subsets that a set has is directly related to how many different rows in a truth table that we have. Because essentially what we're trying to do when we form a truth table, especially when we have, let's say, 2 different statements or 2 different ideas that's within our statement, what we're trying to do is look at all possibilities of what that could be. So for instance, and I'll just make up one right here. So let's say we have P and Q. So these are 2 statements. So we know that P can either be true or false, and we know that Q can either be true or false. Okay? So if we look at P and Q in that light, and I'll actually get rid of this here. Let's say if we look at it this way. So this is going to be P, this is going to be Q, and P could be true or false, Q could be true or false. So the combinations that we can have are true and true, true and false, false and true, and false and false. Okay? And so we see that we get 4 different possibilities here. Well, the same thing happens because we know P and Q are 2 separate statements, so K is 2, and 2 raised to the 2 is 4. And so that's how we know what possibilities we have. Okay? All right, so now let's get into making our truth tables. So we start off with the easiest connective, which is the negation. And this is the unary negation, meaning that we only need one letter or symbol to be able to understand what it means. And so we look at the negation as the opposite. So in doing that, if we know that a statement P is true, then the opposite of that is false. And if we know that a statement P is false, then the opposite of that is true. Moving on to the or statement, this is the disjunction. And of course, what that means to us is this. As long as one of these single statements is true, then everything else is true. So for this row, we see that both are true, so that's true. Here, for this row, at least one of them are true, so that's true. Here, for this row, at least one of them are true, so that's true. And of course, for here, since both of them are false, then of course the result is false. For and, we have the conjunction. And of course, what this is saying is that in order for the entire compound statement to be true, both P and Q have to be true. In other words, both ideas that we are talking about have to be true. So in all these other rows, we see that we have at least one false there, so all of these will be false. Okay. Now, moving on to the conditional statement, this is going to be a little different. Okay. And so with the conditional statement, we said that the conditional statement is true for all instances where, except for when the P is true and the Q is false. Okay. Now, to kind of give you the logic behind this, I'm going to put this in terms of you have someone telling you something, and either they start off telling you the truth or they start off telling you a lie. Okay. So let's say you start off telling the truth, and the thing that comes after that is the truth, then that means everything is true. If you start off telling the truth, and then that concludes to something that is a lie, then of course, the whole statement, of course, is a lie. Now, for these two, this is like saying if we start off telling you something that is a lie, then anything we say after that, whether we believe it or not, we have to assume to be true. So if we start off telling something that is not true and you actually believe it, then regardless of what we say afterwards, we have to assume everything else is true. So that's why we have true here and true there. And so that's how the conditional operator works. Now, I know in real life you're probably saying there's no way this makes any sense, but logically it does. And just to kind of give you an idea of how this works, let's say I said that, hey, today the sky is purple. Okay. Now, if the sky is actually blue today, and I say the sky is purple, and I can say something like this. If the sky is purple, then 2 plus 2 must equal 5. Okay. Now, if the sky is blue and you look at it and you know that it's blue, and you still believe that it's purple, then if you're bound to believe that, then you're also bound to believe that 2 plus 2 is 5. Okay. So, and so that's kind of the thinking or the idea behind this conditional statement from a logical standpoint. Okay. Now, for the biconditional statement, if you notice here, what we've done is we've taken a conditional statement here, and we reversed the letters, and we have done another conditional statement. And here is why. Scroll down a bit. As I've stated before, a biconditional statement is just two conditional statements ANDed together. And so if we're talking about a statement P and Q, we want the if-then that goes this way to be true, and the if-then going back the other way to be true. And so biconditionally, we know that the only way this happens is if both P and Q, well, I should say if both P and Q are true, or if both P and Q are false. And so we form the biconditional truth table by actually using what we know about the and truth table. And so to get the if P then Q, the conditional statement here, we just copy exactly what we see here, because we know when we have true, true, that's true. When we have true, false, that's false. When we have false, true, or false, false for the conditional statement, we know that we still end up having true for the entire conditional statement. Now, to get the if Q then P, one thing that we could do is come over here and actually copy the Q statement again here and do T, F, T, F, and now read it this way. True and true for a conditional statement is true. False and true for a conditional statement is true. True, false for a conditional statement is false. And false, false for a conditional statement is true. And of course, we're getting that directly from this truth table here. Okay? So in looking at that, now all we need to do is AND these two conditional statements together. And we know that the only way that an AND statement will be true is if both the statement here, which we'll call big P, and this statement here we'll call big Q, are true. So we have true, true, so that's true. False, true, it's got to be false. And true, false has to be false, according to what our truth table for AND says. And I'll scroll back up just so that we can make sure that we see it. So for the AND truth table, the only time that we know that an AND statement is true is when both P and Q are true. And of course, for our biconditional statement that we see here, we see that we had true and true here, and true there. All right, so here I just make an extra note about what I've done in order to figure out what the if Q then P statement is. Then of course we can switch these around by just basically copying another column with Q here and just reading it QP. All right, so now what we're going to do is do some examples with statements of the 5 fundamental connectives. So we're going to take some statements, assign them a letter, and then after that sort of explain how this would work from a word standpoint when we use the connectives. So negation. So if we have a statement P that is, it is going to rain outside, then the negation of that is it is not going to rain outside. And from a logic standpoint, we would just represent that by tilde P. Now, a disjunction, again, is like an or statement, whereas a negation is like an opposite. So with the or statement, we're saying as long as one of the two ideas or statements that we say is, let me rephrase that, as long as we know that at least one of the two single statements in our compound statement is going to be true, then everything else is true. So as an example here, if we say Bo knows baseball, if that's true, and we know that Bo knows football, if that's actually true, then of course, in that case, we know that Bo knows baseball or football. Now, of course, we could have a situation where this could be true and that could be false, but this whole entire statement could still be true. But again, the idea of this is to form a sentence or another statement, in this case a compound statement, with the actual word connective. Okay. Now the conjunction uses the word and using the same scenario as for the disjunction, if we formed an and statement in words, this would be Bo knows baseball and football. Okay. Now for the conditional statement, we're going to use situation of I study for 4 hours as one ideal statement, and then the other one is I shall make an A on the test. So if we put that together, if I study 4 hours a day, P, then I shall make an A on the test, Q. And of course, the biconditional statement is reworded. And notice how we have the if and only if in between. So we say, I shall make an A on the test. And this is actually, this should be the other way. So let me split this. This should actually be if Q then P, based upon how I have it set up here. I shall make an A on the test if and only if I study 4 hours a day. Okay? Of course, we named I shall make an A on this test as Q, and then I study 4 hours a day as P. So that's how we actually take the word connectives and form sentences with them. All right, so the next thing that we want to do is that now that we know what our basic connectives are and their corresponding truth tables, one of the things that we can try to form now is a conditional, a truth table for the conditional statement, what's called a converse statement, an inverse statement, and a contrapositive statement. Okay? And so we're just going to do this abstractly first, and then afterwards we'll do a scenario to where we allow P and Q to be something, and then from that standpoint we'll read out in words what the converse, inverse, and contrapositive statements sound like. So the first thing that we need to do is we need to do our first two rows here, which is P and Q. Now you're probably wondering, how do I know to always start with true, 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 false, false, true, false, false? Okay. Now I explained earlier that if I know that I have statement P and Q, I know that both of them only have two choices. Either both of them are going to be true. Well, let me say that another way. We know that P can either be true or false. Q can either be true or false. And so here we can do a little table like this to look at all of our possibilities. So that's one way. But what if we had a situation where we had three of these statements? Okay. Let's say if we had a P, a Q, and an R. Then we know that these are single statements here, so 2 raised to the 3 would be 8. So we would have 8 possibilities, but how would we actually come up with all the possibilities for that? Okay. So I'm going to break away from this momentarily so that you can understand how we come up with these first few columns here, so that depending on, no matter how many separate statements you have, you know how many rows to come up with and what those rows are going to look like. All right, so let's say we have our column P here and our column Q. Now, the way I always start these off is I notice since I have two statements, then I have 2 raised to the 2 rows, which is going to be 4. And so I always start off with the rightmost column before I start, doing, other operations on or other adding connectives to the statements here. But I always start off as true, false, true, false. So I alternate true and false once in this row. And then over here, I alternate it twice. So true, false, true, true, and then false, false, like that. Okay. Now, if I had an instance to where I actually had 3 rows, then I know that I have 8 outcomes. And so here I would do true, false, true, false, true, false, true, false. And then the next row, I would alternate twice. True, true, false, false, true, true, false, false. And here I would do it every 4 times. True, 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 false, 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 false. Now you're probably wondering, why do I know to do this one 1 time, this to do it 2 times, that to do it 4 times? Okay. And so here's the reason for that. We actually borrow what we're doing here from what's called the binary numbers. And so here I'm saying that this row I'm going to alternate my two choices every 2 to the 0 times. And here I'm alternating it every 2 to the 1 times. And here I'm alternating every 2 to the 2 times. Okay. Now, to make my point, what I'm going to do now is actually go over what binary numbers look like. And you're going to see the similar pattern here. Okay. Now, before I do that, though, we're going to cover the number system that we normally deal with. Okay. Now, out of the numbers we normally work with numbers that can be formed by using digits 0 through 9. Okay. And the reason that we do that, of course, is because the number system that we're used to using is of base 10. And the reason for that is that most of us have 10 fingers and 10 toes. Okay. And so we count everything in terms of 10 because that's what we have. Okay. So when we form numbers, we start off by saying 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then after that's done, after we've run out of digits, then we start over and do a 1 here, and then 0, 1, 2, 3, 4, so on and so forth. Okay. Now, what we're doing when we do this is we're actually writing numbers in what we call base 10. And when we say base 10, we're just saying that everything is based upon when we ran out of all of our digits, we reset by using the number 10, okay, so to speak. Now, if we were doing this in binary, this is the equivalent of you just having one stump for a hand, okay? So instead of you having fingers, just imagine that all of your fingers, all 5 of them, are together, and it just looks like one stump, okay? And so then this will be base 10. You can use digits 0 through 9. But in base 2, the only digits you can use is 0 and 1. So if we did that, how we would actually have to count numbers is like this. We would have to say 0, of course, for 0, and 1 for 1. But then when we get to 2, we've ran out of digits, so we have to reset. So we just say 1, 0. And then after that, 3 would be 1, 1. And then after that, 4, of course, we've ran out digits, so we have to go again, say 1, 0, 0. Now, this may be getting a little bit confusing for you, so what I'm going to do is kind of back it up a bit and sort of explain how we form these numbers, and then from that switch it up on you and show you how the binary numbers sort of follow suit. So I'm going to erase some of this to make up some room. All right, so as I've mentioned before, when we form the numbers that we're used to counting or forming, we do it in base 10. So everything is written in terms of tens. So for instance, if I was to do the number 21, say the number 21 here, we know that to get the number 21, we have 2 groups of tens and 1 group of 1. Okay? If we wanted to form the number 508, then we would have 5 groups of 100, 0 groups of 10, and then 8 groups of 1 to do that. Now, if we were to do the same thing in binary operation, it would kind of follow suit here. And so my point here is that when we say ones, here this is like saying 10 raised to the 0, because anything raised to the 0 power is 1. So 10 raised to the 0 is 1. 10 raised to the 1 is 10. 10 raised to the 2 is 100. And 10 raised to the 3 is 1,000. Okay? So for instance, if I wanted to form the number 1,782, then we would have 1 group of 1,000, 7 groups of 100, 8 groups of 10, and 2 groups of 1. Okay. Now, if I did the same thing in binary, it looks like this. I would have 1s, and then I would have 2s, and then I would have 4s, and then I would have 8s, and then I would have 16s. Okay? So looking at it that way, if I wanted to form, let's say, the number 2 here, like how I've shown. So in order to form a number in binary, it would just be one group of 2, no group of 1s, 4s, 8s, 0s, whatever. If I wanted to form the number 3, then I would have to have one group of 2 and one group of 1, and of course zeros everywhere else. If I wanted to form the number 4, then I would have one group of 4 and no other groups. If I wanted to form the number 5, then I would have to have one group of 4, one group of 1, and no other groups. If I form the number, let's say 10, then to get 10, I can do one group of 8, and I can do one group of 2, and then zeros everywhere else. Okay? So by doing that, you kind of see how this all comes together. So what I'm going to do now is erase this and actually write this out formally up to, I think, I'll just try to get as far as I can here, up to 4 digits. So we'll start off with 0, and then this will be 1 in binary, because we have one group of 1 and nothing else. 2 would be one group of 2 and nothing else. 3 would be one group of 2, one group of 1. 4 would be one group of 4 and nothing else. 5 would be one group of 4 and one group of 1. 6 would be one group of 4, one group of 2, and nothing else. 7 would be one group of 4, one group of 2, and one group of 1, because 4 plus 2 plus 1 is 7. And then for 8, I would have one group of 8 and nothing else. For 9, I would have one group of 8 and one group of 1. For 10, I would have one group of 8 and one group of 2 and nothing else. And let me get rid of this here. And then for 11, I would have one group of 8 and one group of 2 and one group of 1 and nothing else. For 12, I would have one group of 8 and one group of 4 and nothing else. 13, I would have one group of 8, one group of 4, and one group of 1 and nothing else. And for 14, I would have, let's say, one group of 8, I would have one group of 4, and I would have one group of 2 and nothing else. Okay? So that's how I would form my numbers in base 2, or my binary numbers. Okay? Now, what I'm trying to get you to see as to knowing for how many statements we have, how do we alternate these rows here? Do you see how, if we start off in the rightmost column, we see 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, continuously repeating, okay? And then in the second row, we see 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, okay? So we see that repeating. I think I did 12 wrong here. So let me look at this again. So this is a group, oh yeah, so yeah, that shouldn't be there, so let me erase that. Yeah, 12 should be one group of 8 and then one group of 4. Yep, so that should be like this and nothing else. And then 13 should be one group of 8, one group of 4, and one group of 1 and nothing else. Yeah, so that's how that should look. So here you see in the second column here, every 2 times you are repeating either the digit 0 or the digit 1. Of course, here you see it every 4 times. So 4 zeros, then 4 ones, 4 zeros, and then 4 ones. Okay. So in the same suit, since we only have 2 choices for what the statement could be, it could be true or false. In logic, these are our digits. So instead of having 0 and 1, we have true and false. And to form our numbers, we'll start off with true, false, true, false, true, false, true, false. Because this 2 to the 0 tells us I need to repeat my digit every 1 time. This 2 raised to the 1 tells me I need to repeat my digit every 2 times. This column here, the 2 raised to the 2, tells me I need to repeat my digit, true or false, every 4 times. Okay? And so that's where this is coming from, and that's why we start off every truth table this way. So I hope that brings some clarity as to why we're doing what we're doing there. All right, so let's go back to the truth table that we were trying to do to try to find the conditional, converse, inverse, and contrapositive statements there. All right, so now that we know where we get these first 2 columns from here, we know how to start off, and then the rest of this is just being able to look at our truth tables and figure out what we need to put there. So we need to first negate P and negate Q, because as we see in some of these statements here, we need to have negations of P and Q. So if we negate P, that's just going to be the opposite of whatever P is. So if P is true here, then that means it's got to be false there. True's got to be false. False got to be true. False got to be true. Okay? And the same thing for Q, we negate that. So we just write the opposite of what we see. Now, for the conditional statement, of course, we've already seen that before, and I'll just do it again here. So we know that true, false, and here true, true, false, false. Okay? So we know here that a conditional statement is true, except for when P is true and Q is false. So we have T, F, T, T. And so now, if we're looking at P and Q and doing the conditional statement, we just copy that thing down, T, F, T, T. Now, to do the converse, we switch these 2 around. And so again, like we did before, we can just copy our Q column to the left of P and then read it that way. And so we know that for the conditional statement, true and true is true. We know false and true is true. We know true and false is the only time where it's false. And we know that false and false is going to be true. Now, for the converse, we're going to look at not P. If not P, then not Q. So we're going to look at these 2 columns now. And so now we read conditional statements just the same way. False and false is true for the conditional statement. False and true is true. True and false is false. And true is true. For the contrapositive, we know we need to switch these things around. So I'm going to do a not P column here. Just going to fit it in there. And then we're going to read these 2 columns for that. And so false, false is true for a conditional statement. True, false is false. And false, true is true. And of course, true, true is true. And so in doing this, we have formed the truth table for both the conditional uh, for the conditional, the converse, the inverse, and contrapositive statements. Now, one thing I want you to notice here is that if you look at these columns, do you see how the converse and the inverse columns are exactly the same? Okay? And so what this means here is that the converse, saying something in the converse and then saying it in the inverse, logically speaking, is saying the same exact thing. Now we also see that for the conditional statement and the contrapositive statement, that these two columns also say the exact same thing. So here, these two are equivalent to each other. Oh, excuse me. I lost my place there, so let's go back. Yeah, sorry about that. So here we know that the conditional and contrapositive statements are logically equivalent, and we know that the converse and the inverse statements are logically equivalent. All right, so moving on to the next page here, we see that a converse statement is equivalent to an inverse statement, like I've said before, and a conditional statement is equivalent to a contrapositive one. And so we see why that is now, since we've um, built our truth tables for all of these different types of statements. Now, in the world of logic, whenever we have logically equivalent statements, we call those tautologies. And so tautologies can be used to state something that is logically the same, but give it either a positive or negative connotation of the statement. So, and I have this example below to try to illustrate what I mean by that. So let's say we have two single statement slash ideas. One is I drink a lot of water. The other one is I have to use the restroom very soon. So for me to be formal, let me go ahead and put a period right there. So if we take these statements and order them conditionally, then it will look like if I drink a lot of water, then I'll have to use the restroom very soon. That would be Q. So this can be looked at as if P, then Q. Now, contrapositively, what we do is we reverse the letters and negate them. So now we know that not Q is going to be the opposite of this, meaning that you will not have to use the restroom very soon. And not P for this is you do not drink a lot of water. Okay? So here, if we look at this statement here is going to be the not Q. If I do not use the restroom very soon, then I did not drink a lot of water. That is the not P. And so we can write that way. Now, the point in this is that when I say if I drink a lot of water, then I'll have to use the restroom soon. And when I say if I do not use the restroom very soon, then I did not drink a lot of water, I am saying the same exact thing logically. The thing is that one of them has a positive connotation to it, one of them has a negative connotation to it. The contrapositive has a negative connotation to it because I'm using negative words like not. Okay? Whereas the conditional statement is void of those things, so that's why it sounds more positive. Okay? And so this is how, logically speaking, we can say the same exact thing, but yet convey a feeling of positivity or negativity, depending upon what we want our audience to experience. So this concludes the first video in the logic theory video series. The next video that I'm going to do, we're going to be practicing building more truth tables, but the truth tables that we're going to build are going to consist of the logic version of De Morgan's law, as well as we're going to look at how we compute truth tables of what we call valid arguments and fallacies. And so we'll define what a valid argument is, what a fallacy is, and show how we can actually prove that a particular compound statement structure ends up being either a valid argument or a fallacy whenever we do the truth tables for them. All right, hope this video helped, and take care, and I hope you check out the next one as well.